Imagine a frozen landscape, vast and still, where the ground beneath your feet has been solid ice for thousands of years. But even in this incredibly stable environment, there is a dynamic dance happening between the ice and the seasons. This dance brings us to an important distinction, one that helps us understand the subtle yet powerful changes occurring in our polar regions. Active layer thawing is distinct from continuous permafrost in a fundamental way. Active layer thawing refers to the seasonal melt and refreeze of the uppermost portion of the ground, which always thaws in summer, whereas continuous permafrost describes the deeper ground that remains frozen year-round for at least 2 consecutive years, potentially 4 millennia. The key difference lies in the regularity and depth of the thaw. To truly grasp this, think of the ground in permafrost regions as a layered cake. The very top layer is the active layer. It experiences a predictable cycle. It thaws in the warmer summer months, allowing plants to grow and water to flow, then it refreezes completely when winter returns. This active layer can be just a few inches deep or several feet, depending on factors like local climate, vegetation cover, and soil composition. Beneath this active layer lies the permafrost, which literally means permanently frozen ground. For ground to be classified as permafrost, its temperature must remain at or below 0 degrees Celsius for at least 2 consecutive years, though much of it has been frozen for thousands of years. The permafrost itself is not just solid ice. It is a mix of soil, rock, and ice, acting like a massive, ancient freezer. When we talk about continuous permafrost, we are referring to vast areas where permafrost underlies more than 90% of the land's surface, often extending to great depths. So, the why is about scale and persistence. The active layers melt is a natural, annual occurrence, while continuous permafrost is defined by its deep, multi-year, or even multi-millennial frozen state. Understanding this distinction helps us interpret the impacts of a changing climate. When scientists talk about permafrost thaw in the context of climate change, they are usually referring to the deepening of the active layer or the thawing of the underlying permafrost itself, which has been frozen for a very long time. A deeper active layer can lead to thermokarst landscapes, characterized by uneven ground, sinkholes, and collapsing terrain, as the ice-rich permafrost beneath thaws and loses volume. This has significant implications for infrastructure, like roads and buildings, which are designed assuming a stable frozen foundation. A fascinating insider detail is the concept of talix. A talix is an unfrozen layer of ground found within or beneath permafrost, or between the active layer and the permafrost. These pockets of unfrozen ground can sometimes act as pathways for water, influencing groundwater flow and heat transfer, making the permafrost system even more complex than it appears on the surface. Another term you might encounter is ice wedges, which are vertical formations of ice that penetrate the permafrost, growing and shrinking with temperature changes, creating characteristic polygonal patterns on the surface. Ultimately, differentiating between the active layer's seasonal melt and the deeper, continuous permafrost helps us grasp the scale of change in polar environments. The active layer's annual cycle is normal, but its deepening, or the thawing of the ancient permafrost beneath it, signals a profound shift with cascading effects on ecosystems, infrastructure, and even global climate through the releases of long-stored greenhouse gases. Recognizing this difference allows for a more nuanced and accurate understanding of the challenges facing our planet's frozen frontiers.